Okay, recording started. So we are monitored. And let me just check. I think, Shada, I will share my screen now. So you don't see the screen in the room, but it doesn't matter really. And if by chance I use the Blackboard, then I will turn the camera in a way that you can see the Blackboard as well. But for the screen, you don't need it. And because I'm sharing now. So let me share the screen here. And here we are in the page of our tutorials. Now I'm clicking on forcing estimation for Harbour design. I just want to tell you, went through all these first three links, but only the third one is delivering information, technical information regarding Harbour engineering. The first two links are just a premise. And if you may have a look, I think they are anyway interesting, but if you're interested in the technical part in particular, of course you are, the first technical lecture was port planning and environmental impact. Now let's click on forcing estimation for Harbour design. And if you go on the bottom of the lecture, there should be a PowerPoint, which is, let's go back, let's go down, it's here. So I'm downloading it because I'm using the PowerPoint to show it on the screen, both in the room and on the PC. So it's a zipped file, but we can open it. Of course, here we are. Okay, and let me pass in presentation. Before I start, just a quick premise on what we are doing today. So in order to make my premise, I go back to the web page. Forcing estimation, it's of course a central topic when we are involved in Harbour design. It's a problem that has many perspectives. We can take several different perspectives to look at it. We will look in particular at the forcing from the sea, because in my lecture last Wednesday, I clarified that when we have to design, in particular, berth structures, we may have loads from the sea, loads from the berth, and loads from the land. And think of, for instance, the actions that are delivered by waves or by currents or by ice jams. These are loads that come from the sea, or ship impact is from the sea. But of course, on the berth, there are also loads like the trucks that are delivering the goods to be loaded into the ships. There are cranes very often, and also there is the self-weight of the berth. Very often they are made by concrete, so you understand that there is significant also self-weight, and any additional exceptional load which may act on the structure of the berth. From the land side, an example is the landfill, because when we build the berth, usually we fill the landward side of the berth with soil, or any other material like gravel, which allows us to build over, to create a kind of strength in the soil to build the roads and then to allow the trucks to pass, etc. All of these loads from the land, of course, are also acting on the berth, and they are generally treated in geotechnics. In geotechnics or structural engineering, you should have dealt with estimation of land loads. The theory is similar to, for instance, what we study for the road constructions or for building retention walls. And the theory is similar. So in order to avoid overlap, I skip this part. I'm not dealing with this. And I am instead focusing on the load from the seaside, load from the sea. It is a problem that is still complicated, even if we focus only on this particular category of loads. It's complicated because there is a random component in these loads, which is not present. For instance, when you compute the loads on the berth, the random component is more limited because we can estimate and we can regulate with the regulations, with the limitation to the traffic. We can, in a way, manage these weights. Of course, there might be exceptional loads also over the berth and from the land, but they are more manageable. The loads that come from the sea have a significant random component. And we know how to deal with it because we already have a background in wave mechanics. On the other hand, uncertainty still is there. And therefore, we have to be prepared also to deal with uncertainty. And I anticipate that I will make a limited use of it, but the probability theory plays a central role when we estimate these loads. As I said, I will not make an extensive use of it because I know that you already dealt with the probability theory estimation of extreme wave heights in other parts of this course or other courses. Anyway, I will stress a little bit some concepts of probability theory, which I believe are extremely important that you have well in your hands. Okay, first of all, before I get into the technical part, I just would like also to remind to the two of you that anything that is asked at the exam, any matter that for the exam is reported here on the web pages. These are the pages that you have to study. Not everything which is on the web pages may be the subject of a question at the exam. And if you are in doubt, just ask me. But in general, there are, when you see that the description is very narrative, this means that this is not something really important for the exam. The exam is focusing more on the technical part of it. So keep a well-defined focus on the analytical relationship, on the maths, and analytical development. In many cases, we will resort to empirical relationship because Harbour engineering and in general coastal engineering is highly relying on empirical relationship. Why? Because of randomness. And in order to deal with randomness, very often we resort to empirical relationships. And empirical relationships have a big problem that they need to be learned by memory. They cannot be really derived through an analytical development. And therefore, I don't really like to ask at the exam questions that whose answers you need to learn by memory. There will be still some empirical relationship which I will mention explicitly, which in my opinion, I think you need to learn. But I will make that clear. In general, when you see an empirical relationship with many coefficients, difficult to memorize, the general rule is that you don't have to memorize them. You just have to be well aware of their existence. But if you are in doubt, please don't worry, don't hesitate to ask me, okay? Just, it's not an inappropriate question. It's a very proper question, like, okay, I understand this empirical law, I understand what's the meaning, what it's about, but should I learn by memory this empirical relationship? It's a very proper question. So if you are in doubt, just ask me. And the final thing, as I said, everything you need to learn is here on the web pages. You may wonder why there is more than what I asked at the exam. The reason is very simple. I think it's important in order to broaden your perspective that you get a lot of information. And also, there are several links in the web pages which you may follow. The links are not in general leading to questions for the exam, but I leave to you, if you are passionate about the topic, if you're interested, the freedom and liberty to follow them. But one important thing is now I am shifting to the PowerPoint. The PowerPoint is conceived just for delivering the lecture, because you see, if you look at the screen now, it's not easy to follow a lecture by reading so many words and so many sentences. This is fine for studying, but not for lecturing. So the PowerPoint is just for lecturing. My suggestion, don't use the PowerPoint to study. it may be, okay, useful for refreshing what you studied, but you may find some questions in the exam which are not in the PowerPoint. They are on the web pages, but not in the PowerPoint. So just be aware of that. And then let's go to the PowerPoint. Okay, so I already mentioned that we have a variety of forcing, which may be originated by soil pressure, vehicles, waves, etc. And I already mentioned that this is the presence of randomness is a problem. And so what does randomness mean? It means that very often you have to rely on observations in order to make your design. And it means that you have to use an inductive approach. Inductive means you start from observing something, you look at the past, you look at what happened into the past, and then from the data, from your past experience, you come to a design. This is often done in coastal engineering, hydraulic engineering. We pick up the worst event in the past. If the past is long, if we have a long history, this is perfectly fine. If we have 100 years of data, of wave data, which is probably never the case, but it is not unreasonable that you take the worst event in the past, or the second worst, or the third worst. It is perfect because this inductive approach basically looks at the history of a context, of a land. There is a limit in doing this, which is climate change, but we will talk about climate change and changes in general. We will talk about them and how to deal with them. The inductive approach is opposed to the deductive approach. The deductive approach means that I write down a theory for describing something, like describing waves, and then the theory allows me to elaborate a model, a mathematical model, and then I get the design event by modeling. And in principle, this approach, if I well understand the physics behind it, if I well understand the dynamics behind it, which is not only physics, it may be physics plus chemistry plus something more. If I well understand the dynamics, in principle, this approach allows me to make predictions with certainty and without the need for data. But the problem is randomness. So there are several examples of physical processes which I can describe with a model, like the time that it takes to an object to, if I drop it, to reach the ground. This is a physical model with very little uncertainty. And so we don't need really to get data for this. I don't need to make an experiment and to drop several objects and see and record the time. I don't need the observations. But when randomness is present, this is an approach that has some limitations, and therefore we have to couple it with the deductive approaches, with the inductive approaches. I start from the data. And just keep in mind that also the empirical relationships, they start from the data. And usually we try to interpolate with an analytical form we have observed. So this is the purpose of this first slide, just to clarify that it is a bit of a problem in Harbour engineering if we don't have any information, if we don't have any wave observation. There is a way, in any case, we will have some rule of thumb, and I will show you some rules of thumb, but in general, the first thing that we have to do is to look for data. Okay, now, before I start, some mention to nautical terms, and let me go back to my web page, because I want to show you one link here. There is a wiki with a glossary of nautical terms, which is linked in the web page. It is very useful. And because there are really several terms used in Harbour engineering and in nautics. And here there is a full list. Like, for instance, I don't know, if we didn't know what a bollard is, we can search here. There is also the search tool. Bollard, just 1 second, I get there. Body, bollard, here it is. And if you click on bollard, very often it is shown a picture. So It is indeed a useful page, this one. And so let me go back to the PowerPoint to look at this picture here, and just please learn these definitions. This may be asked at the exam, because they are very relevant for the design of harbors and berths. So, by the way, if there are terms that I am using which you don't know, or maybe you don't understand for my English, just stop me, okay, and ask me what is the meaning. So, please, you see here 6 definitions. So the beam, which is indicated here with B, you understand what is that. And the length overall, this is which is OA in the picture, and overall length of the ship, okay. And there is the waterline length, so it's WL here, W/L. And the waterline is the blue one, okay? And the length between perpendiculars, PP, it's shown there. And the draught or draft, which is D, it is the distance between the waterline and the bottom, the keel of the hull, sorry, the hull of the boat. And there is also the freeboard F. So just learn these terms because they are recurring in our discussion. And we will see other nautical terms. You can find them in the glossary of nautical terms, which I mentioned just a few minutes ago. Now, mooring loads. And mooring loads means the forces that are acting on the bollards through the spring lines of the boat. The spring lines are the ropes that connect, that are used to fix the boat, the ship at the berth. We will mention spring lines also later. So through these spring lines, the ship acts, give forces over the bollards, and these are caused by the fact that the ship actually it is floating in the sea, and therefore it is subjected to the action of wind on the sides and also along the transversal section of the ship. It is subjected to the action of waves, and the waves can tend to move the ship in the vertical direction and in the 2 horizontal directions. And also there are currents. There are currents which we can find also within an harbor. And we will consider these 3 actions, and we will see some empirical formulations for estimating the action of wind, the action of waves, the action of currents. The empirical formulation are very similar, have a physical basis, and we will see them. On the other hand, they include a lot of coefficients and they integrate empirical solutions. We will not consider the loads originated during berthing because these are temporary loads. We are not considering them. There are a lot of references if you are interested. It depends, of course, on the size of the ship. It depends on the type of harbor, on the type of maneuvering that ships are allowed to use when they are berthing. There are links in my webpage to open access material, which delivers useful information if you are interested. All the links that you can find on my web pages are open access, and everything you find in general on my web pages is open access. What you find in Virtuale may be not fully open access. So when I have something that I cannot really make open access, I put it on Virtuale. And but I make an effort to make everything available in terms of tutorial by using open access information. Okay, now, first of all, some rules of thumb. And as I mentioned, it is useful to know them because it allows you to make a check of the result of your computation. And so it is extremely important. The order of magnitude of the forces that we are estimating, it's extremely important that you get it. And these guidelines are derived by national rules, national guidelines, which I found for different countries. Keep in mind that I mentioned this last time. When you get entertained in the design of an harbor, you have to check what are the constraints, what are the rules that you have to follow, the codes of practice. And we may distinguish between international standards, or let me go in order of their enforcement. Let me call it this way. First of all, there are the national rules. If you have any national rule, you have to national or international rule. The rule means law in force, means regulation, and you have to get aware of any national or international regulation that is conditioning your design activity. And it depends on the country, actually. Some countries have regulations, some others not. In general, the countries may have different restrictions. Of course, if there are international codes and they are compulsory, they apply in the international domain they are designed for. But the national rules can be different. It is interesting also to look at the standards, national and international standards, and guidelines. Guidelines are more compelling with respect to standards. So the most compelling, of course, regulation is given by the law in force. And then there are the guidelines. If you disattend a guideline and something happens, you may be judged guilty because you disattended a guideline. Even if it's not restrictive, when you disattend a guideline whose value is recognized because it is promoted, for instance, by an authority who is not posing a formal limitation, but only guidelines, this should not be disattended. And then you should look at the international standards, because if you don't have any rule, if you don't have guidelines, it's a good thing, it's a good advice that you look at the international standards in order to be sure that, in order to make sure that you are following what is considered common sense. Now, here there are some numbers which are derived from international guidelines. If you look on my web pages, there is also the link to the reference, and also you can download these guidelines. So for design ships, design ship is the ship which I am designing the harbor for. Okay, so it's extremely important, of course, when we have to design an harbor, that we clarify, we get information on the tonnage and the size of the ships which may use it. Of course, a touristic port is very different from a cargo port, because the tonnage and the size of the ships is different. If you want to design a berth, and we talked of the suggested size, suggested length for berths, for piers, for wharves, they depend on the length overall of the ship. So if you are designing a berth for hosting cruise ships, you know that they can be more than 300 meters long. So of course the berth should be longer than that. Okay. So once we have information on the ships, on the design ship, if their tonnage is up to 20,000 tons, each mooring point can be designed so that it resists to the following minimum loads. So these are suggested minimums Horizontal pull ranging from 10 to 100 tons, depending on ship displacement and type of load, and vertical pull, which is about 50% of the horizontal pull. And they are assumed to act at the same time, so they can be concurrent. And this is quite understandable. This is quite reasonable because when a ship is moored, we may have concurrency of vertical and horizontal pulls. And the pull load should be considered to occur at any angle with the berthing front. And of course, we have to select the worst condition, so the less favorable condition. Good. So you have an idea here, and you understand that bollards must be designed to against a significant force. When we talk about tens of tons, of course, it's a significant force. And for design ships that exceed this 20,000 tons displacement, the assessment of the mooring loads should be carried out by considering all possible forcing operating at the same time, which means that you have to carefully evaluate the concurrency factors. Concurrency factors are express the probability of two loads acting together. And the concurrency factor basically allows you to decrease some of the loads if you assume that they are occurring together. And when the ship becomes over a certain tonnage, here is 20,000 displacement, these concurrency factors cannot be decreased much. We have to assume that because, of course, the consequences of an extreme event, which is given by the concurrency of several factors, it's more concerning, this occurrence, if we deal with big ships. And this is the Spanish standard, which I was referring to. Let me see if it opens. I think so. Let's see. And yeah, okay. Here it is, still available. Perfect. And I found it a well done guideline, and I didn't find anything which is similar in Italy and open. This is open, is not old, it's quite recent. I don't remember the date. Okay, it's 30 years old, but not so much. And here there is a lot of discussion about the project and design life, things that we are using here. And here you see there are the actions. And it is quite long, more than 250 pages. Okay, let's close this and also this. And yeah, PowerPoint, here we are. Okay, so wind forces, let's start with the wind forces. As I said, wind is putting pressure over the ships. The ships have a large surface, which is mainly concentrated along the longitudinal axis of the ship, but also on the transversal part of the ship, there is a considerable surface that is exposed to winds. In general, I start with wind forces, and my discussion is more focused on wind forcings because these forcings are, in general, more stressful with respect to the forces due to wave and currents. So usually the wind is the main component. Of course, you may have exceptions, and depending on the local context, but in the great majority of the cases, this is the higher forcing. Now, so wind forces. What is the big question mark here? it's not really the surface of the ship. The big question mark is to estimate wind. And we rely on observations. Wind, it is a component that, a weather behavior that is extremely difficult to predict and quantify from a technical point of view. Usually we can predict with the meteorological prediction the occurrence of strong winds, but making a prediction, especially in the long term, of the extreme wind that we may expect in a location, it is complicated, and it is something that is usually done statistically by analyzing wind data. And this is why very often we see anemometers in the ports, in the harbors. We see anemometers for the very reason that we need to assimilate data continuously. Also, the anemometer serves as an alarm, as a monitoring system in real time. But the data are not only used in real time, they are also used offline to continuously update our knowledge about winds. In general, we refer to wind data that are recorded at a distance of 10 meters with respect to the zero level, to the sea level, above ground, let's say. Ground is generally a couple of meters above the sea level. And so the requirement is that the anemometer is placed 10 meters above ground. It is extremely important that the height of the anemometer is specified, because it's a completely different story. And we understand that. If when we are in the mountains, when we are in the bottom of the valleys, the wind is generally lower than on the crests, on the ridges. Now, of course, the longer the record and the more reliable the wind estimation is. What does it mean, wind estimation? It means that we describe with the probability distribution two main things: the direction of the wind and its intensity, its velocity. So we have two data that are important. It's not only the velocity, but also the direction, the dominant direction. Why the dominant direction is important? You may think that it doesn't matter from which side the wind comes. Actually, this is not really true, because wind, it is also a problem when mooring for the berthing operations. And it is definitely better if you have to moor a ship to get the wind in the same direction as the berth front. So if the wind is parallel to the berth front, it's less disturbing with respect to the wind that is perpendicular. And this is clear why. Because when the ship gets closer to the berth, you want to avoid that there is a violent contact, a violent approach, damaging approach. And if you have wind pushing the wind, of course, you can, the longitudinal part, the side of the boat may collide with the side of the berth. So knowing also the direction is extremely important. And one recommendation, in fact, for harbor design is to align the berth with the main direction of currents and the main direction of winds, for this very reason. Now, what is the windrows? The windrows is describing the probability distribution of wind velocity in the different directions. So let's look at the windrows with more detail. This is an example. This is the windrows at LaGuardia Airport in New York. So what do we see here? Let's try to, I have several slides because I think it is important that we understand the meaning. So don't worry, you don't need to get it in one slide only. So what can we see here? First of all, we need there is a dominant direction of the wind, two dominant directions. One is the south direction, and the other direction is northwest. Okay, northwest, yeah. And then there is another dominant direction, northeast. Now, what is describing the windrows? So let's focus on the south direction, which is the direction where we have more the dominant wind. First, you see in the center of the rows, there is a blue circle, with an indication of 3.6%. What does this mean? It means that it's calm situation. So with respect to the total observation period, we have about 4% of the time where there is no wind. So this circle then extends over all the directions, and it's the basis for all the directions. So in the south direction, we have a 3.6% with no wind, which is the same in the east, of course, because there is no wind. And then you see that there are circles corresponding to 2, 4, 6, 8, 10, and 12%. So if I go in the south direction, I see that I have about 2% plus, let's forget about the 3.6, okay? This is the zero. And then I have an additional 2% with wind between 0 and 1.54 meters per second. And this is about 2%, because you see that the dark blue gets just a little bit over the 2% circle. And then we have up to about the 8% circle, which a wind that is between 0 to 5. So the 8% means 0 to 5. If you subtract the 2%, it means that you have an additional 6% between 1.5 and 5. And then you have the gray one. The gray one goes up to about 12%. It is wind. Let me see the color. It is difficult to distinguish between two greens. Anyway, there is a first green which goes up to 11.5, I would say, which is from 5 meters per second to 8.23, and then another green up to 1080. So this means that I have a percentage of 12% of wind from 0 to greater than 0, let's say, to 15 meters per second, plus a 3% in which I have no wind, which means about the sum is about 12 plus 4, 16%, which is the percentage of time the wind is blowing in the south direction. So these percentages of time are frequencies. Okay, so when I say 4% no wind, it means that I have a frequency of 4% of no wind. Frequency can be assimilated to probability. And therefore, this means that in each direction, through the windrows, I can estimate the probability distribution of the wind velocity, which is the information that I need. I think I already commented on this one. Yeah. Okay, yeah, there is, if you look at the legend on the right part, there is, besides the wind velocity, there is also the average frequency each velocity range occurs. And in principle, if we make the sum of these frequencies apply over all directions. So if I make the sum, I should get to 100. Actually, the sum gets to about 96%. Why? Because there is something exceeding this range of monitoring. So maybe that there were some strong winds that were not included here, or some winds that are not included into this scale. But the sum is more or less 100%, and for some windroses you may find 100%. And here you see it's explained here. They do not sum precisely to 100%, as winds that do not fall in the considered ranges are sporadically observed. Okay. Now, how can we determine, for instance, along the south direction, the probability distribution? Let's just one. Okay, I think I already made these computations, just discussed. This is something just to clarify. This is the probability distribution. So along the south direction at LaGuardia, the probability distribution sums up to just a little bit lower than 16% because in the south direction, I have the 16% of the winds. Of course, I could represent the same probability distribution by looking for the vertical axis only at the south direction. And in this case, it would sum up to 1, more or less. And 1, because here it's in percentage, so 100, okay? And this is the cumulative probability distribution. I think you are aware of what the probability distribution is, but anyway, I will make some considerations on it. The probability distribution allows to estimate the return period. Of course, we have to know the time step of the observations. So one thing is if you have one observation per year, and one thing is you have one observation per hour. So the unit of time is to be considered, because the probability distribution means to allows you to estimate the frequency of extreme events. And so if I have a frequency of 1/100 and the time step is 1 year, it's never 1 year for wind, but let's just make an assumption. It means that a frequency of 1/100 is more or less corresponding to a return period of 100 years. It is the highest value that I observed in 100 observations. Given that any observation is observed once a year, it means that the highest value, if I have 100 observations, the observation period is 100 years, the highest value occurred once in 100 years. So the probability distribution giving to you an estimate of the frequency allows you to estimate the return period. Of course, you know, I think this, but I just want to stress the concept. If you have observations for 100 years and you estimate the probability distribution, and then you use this probability distribution to compute extreme value, extreme wind velocity for a given return period, you have to be careful of extrapolation. So if I have 100 years of observations and I want to estimate the extreme wind for a return period of 200 years, I can use the probability distribution, but I need to extrapolate it. Because if I take only the highest value, as I said, it corresponds to a return period of 100. If I want to estimate the value for a higher return period, I am extrapolating. You may wonder, how can I extrapolate an empirical curve? Because this is an empirical curve. Actually, you know that probability distributions have an analytical relationship. They can be used to fit the empirical frequency curve, and then I can use them to extrapolate. Be careful, because any extrapolation, as you know, any extrapolation of random processes entails uncertainty. And if you use I make an exaggeration, 1 year of data to estimate, of wind data, to estimate the wind with 100-year return period, you can extrapolate, but it is not reliable. So be careful of the quality of the data that you have, quality in terms of both uncertainty and length of the observation period. Whenever you use data, you have to be very careful, very mindful of the so-called metadata. So the additional information, the associated information, how was it measured, the height of the anemometer, if it's 10 meters is a different story with respect to 2 meters, etc. Just a few words about probability. I'm not going into the details. I just want to say that I already mentioned that probability is basically frequency, which is a very simple way of defining it. This is called the frequentist definition of probability. So if I look at wind data, I look at their frequency and I assimilate this frequency to their probability. On the other hand, we have to be fully aware that there is a huge theory behind it, which is elaborated just for the purpose of minimizing the underlying uncertainty as much as possible. And I also want to inform you that one can define probability in many ways. Probability means likelihood. Usually, the axiomatic theory is, which you see on the screen, is the approach that is most used. Basically, the axiomatic theory was defined in this way because it leaves to you a lot of flexibility to adapt the definition of probability to your needs. And I explain better. Let's suppose that we stick on the frequentist definition. This is fine. But if you don't have data, how can you use a frequentist definition? You may know that there is an alternative to the frequentist definition, which is the Bayesian definition. Bayesian means that you use your expert knowledge. And we use it every day to make predictions. Very often, we make predictions basing on our expectation. Expectation means a Bayesian approach. You gain a prior knowledge. And then there is a lot of formalities in how to make sure that your perception is objective. Okay, because this is the problem. I mean, perception may be subjective. Numbers are less subjective. Also, the numbers can be subjective, but the perception can be subjective. And of course, we don't want to run the risk of getting trapped into biases. Subjectivity very often means bias. And so in order to avoid this subjectivity in the Bayesian approach, there is a lot of formal theory that has been introduced. So we are not dealing with it. The graph that you see here is an interesting representation of a frequentist approach to probability on the other end. And it is the probability function that specifies the probability distribution for the sum of counts from two dice rollings. So you roll two dice, and then you take the sum of the outcomes. So basically, how many results can you have for the sum equal to 2? Only one. You see on the left, you have to get 1 and 1. And the probability is very low. It's 1/6 for getting 1 times 1/6 for getting the other one. So this is 1/6 times 1/6 should be something like 0.02 more or less. Sum 3, we have two possible outcomes and so forth. The more likely outcome is 7, because if you look at the combinations, and we can define this by using theory. It is very easy because there is a simple law of probability that allows you to analytically compute the probability density, the probability mass, sorry, of the outcome 7, which is about 0.16. It is quite a significant probability. It means that if you try 100 times, on average, you get 16 times the result of 7. On the other hand, you can compute the probability very easily with this scheme. Keep in mind that probability, which is something that usually looks nasty, it's nothing else that common sense. It's a formal way to draw conclusions from experiments. And it is fascinating. Anyway, so how can we define probability in a very flexible way in order to include the Bayesian approach, frequentist approach? Now, Kolmogorov developed these axioms, which I think, in my opinion, they are really enlightening, and defines probability in this way. The probability of an event is a real number greater than or equal to 0. So it cannot be negative. Okay, very simple and trivial. Second axiom, the probability of at least one of all the possible outcomes of a process, such as rolling a dice or a die, it depends on the English. So the probability that at least one result occurs is 1. What does this mean? It means that the probability is varying between 0 and 1. Because, of course, if you roll a dice, what is the probability that you get a result between 1 and 6? It's 1. Okay? So probability is varying between 0 and 1. And the third one, it is the most enlightening, in my opinion. If two events are mutually exclusive, then the probability of either one of the two occurring is the probability of the first one plus the probability of the second one, which is the additive property. So basically, if you think of tossing a coin with these three axioms, you easily understand that the probability of getting a tail is 0.5 and the probability of getting an head is 0.5, because the probability that you get at least one of the two is 1. And then, given that the probability of the tail plus the probability of the head should be 1, you easily understand that, of course, you could say that the head could be 0.3 and the tail is 0.7. And at this stage, you have to come with either your expert knowledge, like you look at the coin and you say, no, the coin is balanced, so the probability must be equal, or you make an experiment. You toss the coin 10 times and you easily estimate the probabilities. These three axioms, make an effort, please, to remember them, because they are really the basis for probability. I will not discuss probability much more. And I hope that you are familiar with cumulative probability, which is this one, probability density, which is the derivative of this, and probability functions, like the normal distribution, the gamma distribution. I think that you had already some background on that. In any case, on my web pages, there is a box here. Yeah, probability, which describes also what is a probability density, what is a probability distribution, frequency definition, the axioms, and the Gaussian distribution. Okay, and just refer to it, and if you have any question or you think there is something that you are missing, I want to turn the phone off just 1 second. If there is something that that you are missing, just let me know. Okay, here it is. Okay, good. Now, let's move forward with our wind data. So probability is done. Now let's look at our wind data. This is the Beaufort wind force scale. Make an effort to, not all of them, but just to get oriented in this scale. You see the velocity on the horizontal axis, and what you see there, first of all, the fact that the line is carved rather than rectilinear doesn't matter. On the y-axis, on the vertical axis, there is nothing here, okay? And the numbers are the scale of the wind, while the names are, so the Beaufort wind force scale in knots and in meters per second. You have the knots above and the meters per second below in the bottom. The Beaufort wind force scale is expressed in numbers, and the names are the terms that are usually used to describe in words the scale. Okay, and so when we see a moderate breeze, a gale. A gale has a velocity of about 20 meters per second. It's already 20 meters per second means something like 60 plus like 70 kilometers per hour. It's a wind that it's already, I mean, you can still walk, but it is not so easy. And the hurricane, it's you see that corresponds to more or less 35, which means 100, more than 100 actually. It's 120 more or less, a little bit, yeah, 120, which means that you cannot even walk in such conditions. It is interesting, this Wikipedia page, let me open it. Because just see. Okay, here it is. And this is there is an interesting picture. This one. This is taken a ship in a force 12, a hurricane force. You understand that the waves are a little bit. There are some nice pictures on the web of waves. There is a link in my webpage of coastal engineering of wave height and pictures. There is a webpage showing pictures of wave of increasing height, and it's very nice because you understand that you know, a wave. When we talk about a wave of like a couple of meters, you think that it's I mean, it's not a big wave, but actually when you look at the picture of a wave of a couple of meters, you know, it's taller than us, so it is impressive. And so this is describe the scale, the history, and the picture. You see, this is interesting. This is what the reason why I said it's interesting. You see different sea conditions with different wind intensity. It is very nice because what I really recommend to you is to get a perception of this phenomenon, to look at them. So it is interesting. I'm also teaching floods, and I always tell students, when you hear about a flood, try to go and see, because of course you have to be careful, because when you get close to a risky situations, risky context, you have to be very careful. And in fact, very often the authorities invite people to stay away from them. But on the other hand, if you have an opportunity to go there and look at a flood or look at a sea condition that are extreme, I think it is very instructive. And we are lucky today because we have the web offering opportunities to see pictures, to see videos. And can you imagine, up to 30 years ago, there was no opportunity for this. Okay, there was the television, which by the way came less than 100 years ago, and the television, but it was not possible to have access to databases. So if you had a chance to see on the television, it was okay, but then you couldn't go back. And now on the web, there is a lot of information, which I really invite you to use. So we talked about a moderate breeze, I think, first. And you see here, this is the Beaufort Force 4. It is in open sea, and it is not so easy to perceive the height of the waves. This is taken from a big boat. So it is called small waves, and I think height is, it's written here, wave height is from 1 to 1.5 meters. It's already, anyway, a busy situation, but in this case, you see height is from 2 to 2.5, and this is the force 5, and then force 6. This is starting to become a little bit impressive. You see 3-4 meters, and then force 7, and it's for about 5 meters. Force 8, it's up to 7 meters. Just 1 second. Force 9, and this is 10 meters. Waves of 10 meters, it's like a building of 3 floors. I mean, it's really. And then 10, 11, and 12, the previous one. This is indeed interesting. Okay, let's go back here. So try to usually I'm not asking at the exam what is the velocity of a violent storm, of an hurricane, but I really encourage you to get a perception of what it means. And another thing that, in terms of velocity, and another thing that I suggest you to learn is the correspondence between knots and velocity with the international units. So a knot is about 1.8 kilometers per hour, which means it's in terms of meters per second, a knot is about 0.5 meters per second. Just try to get this with the units. You have to get used, because the knots, it's a unit that in nautics it's still largely used. Before I move forward by talking of wind, let's clarify what is a ballast and when we say that a ship is in ballast. So the ballast is the weight that a ship can carry on to increase its stability, especially when it's unloaded. So the ships are usually equipped with an internal tank which can load water to increase its weight, because the ship has the need of varying its weight, because when it's loaded, then of course the drought increases, so the level of the water raises on the sides of the ship. And of course, we cannot allow the drought to increase too much, because otherwise the ship sinks. And then when it is fully loaded, usually the ship releases this additional weight. When it's unloaded, the ship, in order not to lose the stability, it loads water, loads what is called the ballast. And a ship is said to be in ballast when it's carrying ballast only. So when we say a ship is in ballast, it means that the ship is unloaded and there is only the ballast. And this is the most exposed situation to wind. So the ship, the most dangerous situation with respect to the wind is when it's in ballast. Because the surface of the ship that is exposed to wind is maximum. So the most dangerous situation is not when the ship is loaded, it's when it's unloaded, because the ship raises up and therefore the out of water surface increases. Okay, so wind forces. First of all, the computation is very frequently regulated by international or national regulations. So get aware of that. What I am now proposing is taken from the Spanish regulation, which is more or less, I would say, the same as in Italy in general terms, but the coefficients that we will see are introduced in the computation may be different. So first of all, we have to compute the wind velocity, or the design with wind velocity, the event wind velocity. Okay, when I use the term, I want to be clear. When I use the term design wind velocity, I mean, design wind velocity, I mean the velocity of the wind that is adopted in order to size our structures and infrastructures. I make this clarification because I think that design velocity is not a correct English term. I asked several colleagues and the native speakers told me that they prefer to use design event, not design variable. So not design velocity. They prefer to say design event in English. Design event. Design event. I mean, the event the project is designed against. And in Italian we say variabile di progetto, which means design variable, because project we can use design in English. And so I think that it's understandable if you say design variable in English, but actually I had this doubt. I asked my colleagues and they were really thinking of it. They didn't have a ready answer to give, but they said, design variable is not really what we say. We prefer to say design event. Okay, anyway, I think we understood each other. Wind velocity, the wind velocity that is used for our project. Of course, it depends on climate, and we estimate it from the data. It depends not only on climate, also it depends also on the harbor. And in fact, when it's possible, we try to settle down the harbors in some sheltered areas, because of course wind it's a problem. It's a problem because also it generates waves, and therefore we try to place the harbors in safe places. But on the other hand, there is also the design of the harbor, its extension. They may be relevant. So the design wind velocity, first of all, should correspond to a return period. We will talk about return period later, which means an assigned frequency of occurrence, an assigned probability. And on the other hand, it should correspond to the max velocity of the gust that may affect the considered ship. So you know that the wind velocity is variable. Variability means that if you measure the wind velocity over a time frame, you average the wind velocity over a time frame, you get an average that is lower than the max during that time frame. So, for instance, the wind velocity is generally measured as an average over 1 minute, but then it means that if you look at 10 seconds, you have an higher max. For this reason, we very often need to introduce gust coefficients to compute the max wind. So here you read that usually we are recommended to use a 30-second gust wind velocity, which means that if you have data that are recorded over a 10-minute period, which means average over 10 minutes, then you should increase, in order to scale down from 10 minutes to 30 seconds, you should increase the max wind of 20%, which means that the gust coefficient is 1.2. Today, we have increasing availability of data at fine time resolution. So it is very likely today that you can find, for the most recent times at least, wind data with a resolution of 10 seconds or 30 seconds. In the past, usually 10 minutes was the time step that was considered. And when you have an observation every 10 minutes, this is not the max. We assume it's the average. It's not the max, because if you have just points in time, it's very unlikely that you get the max of the observation in these points. Maybe that once at a time you get the max, then you could get the minimum, but then you randomly vary, you randomly pick up numbers between the max and the minimum. And this is why we consider it's an average, even if it's not really a computed average. But when we have a discrete time monitoring, and in the past this was the case, a discrete time monitoring is assumed to be representative of the average. So we have this GAST coefficient to introduce. And I mentioned the GAST duration of 30 seconds. Usually, this is the GAST time that we adopt. We are recommended to use. You have to see the regulations, of course, but very often you will see that the order of magnitude is 30 seconds.
Good morning, Prof.
Yeah, please.
I'm just entry now because I.
No problem. No problem, Giorgio, correct?
Yes.
No problem. And I started at 2:15, so I'm making the break in 15 minutes. I have a person in the class, and you are two attending online.
There is one person in class?
Yeah, yes.
Huh. Okay.
I don't remember your name. Nemran. I'm not sure if you know each other.
Nemran, okay.
Keep in mind, Professor Archetti wrote in the chat, she's a little bit sick, so tomorrow she will teach online.
Yes, she told me.
Okay, very good. Actually, about me, I am planning to continue to come in presence here. Just keep it in mind. I'm not saying that because I ask you to be here. It's no problem. Just make yourself comfortable. I just wanted to inform you. Okay.
Okay.
And maybe if this is something that I could say to all students, you included, maybe that I think there are no additional students that I am expecting attending these lectures. Maybe that if you foresee that you are not attending in presence, I may appreciate if you send me an email like 2 days in advance, like, Professor, I will attend online. We still have 6 lectures to go because you know, if I know that nobody's here, maybe that I take the opportunity to teach online because it's also easier for me because I can use the graphic blackboard. It's less boring. Okay. Now, wind forces again. So, orders of magnitude, once again. So the Spanish rule, the Spanish standard, recommends to adopt a minimum wind velocity of about 20 meters per second with a gust factor of 1.2. It's 22 actually. So if we don't have the opportunity to make a closer investigation, this is what the Spanish standard suggests. So 22 times 1.2 as gust velocity to be adopted to support our project. And the same rule suggests to adopt a wind velocity of about 17 meters per second for mooring operation in normal condition. And other international standards suggest to adopt a minimum velocity of 30 meters per second for computing mooring forces with a gust factor of 1.2. So you see the Spanish standard is from 17 to 22 meters per second. And other standards suggest higher wind speeds. This is perfectly understandable because when we move in other places, of course, the behaviors of wind are different. So we shouldn't be surprised. And also the change is included into plus minus 30%, more or less, which is okay, I mean. And in any case, the message here is try to get aware of the regulations that may affect your specific project. On the other hand, to set up an upper limit, it is not recommended to use a max wind velocity exceeding 40 meters per second with a gust factor of 1.2. Which corresponds to already a significant pressure about, we will see a graph later on, but it's about 1.4 kilonewton per square meter, which is, I mean, it is really a huge pressure. Because we have to take into account that in any case, if the ship gets into difficult conditions, there is a B plan that can be adopted, and the B plan is to unmoor, so to leave the springs in order to let the ship free to move and to better respond to the pressure of wind, because you understand that when you can, in a way, move, the action of the wind is softened. If the body is rigidly linked to the land, then the action becomes less elastic. By the way, the springs have some elasticity precisely for this very reason, because a rigid connection would would translate into mooring forces that are amplified. Usually, the ships leave the berth when the velocity of the wind exceeds 25, 30 meters per second. They tend to leave the berth. Of course, this is not always possible. Think of a crowded harbor. It's not possible for everybody to leave the berth. It also depends on the ship conditions, whether the ship is in ballast or not. And or they have also a C plan, which is to take in ballast. If they have this opportunity, the ship may be loaded and therefore without ballast. And if a critical situation occurs, then the captain can load ballast in order to reduce the exposure of the ship to wind. So usually wind velocity of no more than 30 meters per second are considered a good choice. But once again, look at the specific context and specific regulation. Now, this is the formula. So let's put it on the screen. And this is actually the wind force in kilonewton. On the left-hand side, you see PW. It's the wind force in kilonewton. Okay. So let's first make some reasoning on the wind force. The wind force must be dependent on the surface, on the area of the exposed surface. So we have to find the area here somewhere. The wind force should also depend on the velocity of the wind. Squared, because we are engineered, we know that the pressure that is given by any fluid against a surface is proportional to the square of velocity. So we must find the velocity squared somewhere here. Third, the wind force depends on the angle between the wind and the exposed surface. If the wind is parallel to the exposed surface, we are happy. There is no wind force. If the wind is perpendicular to the surface, we are unhappy. And therefore, the angle between the wind and the ship, whatever defined, should appear here. And then the wind force should depend, but this is a weak dependence because it's not really much variable, should depend on the density of the air. Okay, but this is not really a big issue because the density of the air is more or less the same. Okay, and then we said this is the physics of it. Okay, we know from the physics that the force should depend on the area, should depend on the velocity squared, and should depend on the angle, of course, and the density of the air. And then we expect some coefficient in order to adjust the estimate in an empirical way. Good. Now, let's look at this formula, which is very simple. If you could make an effort to learn it, this is one of the few empirical formulations which I'm kindly asking you to learn, because once that you learn this one, then also you learn the other ones which allow you to compute the action of waves, the forcing due to currents. They are very similar. So first, CW is a wind force coefficient, and now we have the question how to estimate it. But this is an empirical coefficient in order to correct for uncertainty or whatever. Now, AW is the side area of the ship above water, projected over the ship longitudinal plane in square meters. So again, side area of the ship. And then there is another area, the front area, BW, of the ship, again, above water. We are not concerned of the area below water, of course. Wind is above water. So BW, front area of the ship, front, not side, in the transversal direction then, above water, projected over the ship transversal plane. Okay, so just keep confidence, gain confidence with this term, longitudinal plane of the ship. It is intuitive, but anyway, it is easily understandable, but anyway, longitudinal plane, transversal plane, okay, again in square meter. And then we have the angle of the wind direction to the ship center line. And let's see how it's defined. I move forward one slide and then I come back. So this is phi. It is defined in this way. So you see the longitudinal direction of the ship with the longitudinal axis, which is the red one, the red dashed line, okay? And then there is the transversal direction, which is perpendicular to the red dashed line. And then here you see how phi is measured. It's the angle, the acute angle between the wind direction and the ship center line. Okay, and then I'll come back on this figure because you see that there are also the spring lines which are numbered. I will show you the figure later in order to learn the names of these spring lines. The spring lines are the ropes connecting the ship to the bollards, to the berth. Let's go back. So the angle is here, and of course we use the sin squared in order to compute the side component of the wind force and the cos squared in order to compute the component in the orthogonal direction. And then there is the component of the pressure. We need the pressure here. So far, let's forget about CW, which is a coefficient. We only computed the area exposed to wind, which depends on the side and transversal area and the wind direction. Now there is the pressure component. By multiplying pressure by the area, we found the force. The pressure component is square wind velocity, VW, divided by 2g, g is gravity, and multiplied by the air density, specific gravity of air, sorry, okay, not really the air density, but okay, it's connected. Specific gravity of air, okay, and g is acceleration gravity. That's it. It is easily understandable, the physics. There is the question mark of estimating CW. So let's skip this slide for now. And before talking about CW, let's talk about the computation of AW and BW, because if you have a well-defined shape of the ship to support your project, of course, you compute AW and BW easily. But in absence of information, because you may be left with a variety of ships or limited information on what ships are to be expected, you can use these relationships here, empirical relationships, where P and LBP are the beam and the length between perpendiculars of the ship. And then here there is a link. I'm sorry that I have to check, because if it is wrong here, it's also wrong on the web pages. Just 1 second, I want to check. Yeah, here there is a link that has been well defined, badly defined. I will correct it, okay? Anyway, the link is visible, but what is G? G is the ship's freeboard, and which is the ship depth minus draught. The freeboard, anyway, we defined it in my first slide. Y and Z are mean height of the transverse and longitudinal area, respectively, of the ship's superstructure above deck. Now, we can adopt average value for these variables, for these independent variable, like the length between perpendicular is more or less of the same order of magnitude of the length of the berth. So usually this measure is given to us. And once that we know the length between perpendicular, we can also find the guidelines on the web, which may suggest ideal value for G, Z, and Y, ideal, let's say proxy values for G, Z, and Y. So the meaning of these two equations, which you don't have to remember by memory absolutely, is that for estimating the typical values to be taken for A, W, and BW, you can refer to literature indications. Okay, good. So when should we expect the max wind force? And then I'll make the break shortly. When phi is 90 degrees and the wind blows perpendicular to the ship center line. In this case, the formula reduces to PW. It's given by CW times AW, side area, times P, where P is the wind pressure. Okay, wind pressure, which is equivalent to gamma W times velocity of the wind squared divided by 2G. Good. Okay, let me look at the next slide. Here you see a graph, I made it, which gives the wind pressure for different wind speed by adopting a density, a standard density for air. So the pressure is given by this formula here. If we take a standard value for gamma W, then the pressure only depends on the wind velocity. So it is relatively easy to make this graph. And just take into account that here we have the lower curve, which is actually giving a higher pressure than the upper curve, because the pressure is in the horizontal axis. So the lower curve takes into account the gust factor. And here you see the velocity on the left in meter per second. And on the right, you see the Beaufort scale. And I found this graph interesting, so I remade it because it was not public domain. I found it on the web, was not public domain, so I remade it. And it gives to you a very quick way of estimating the wind pressure, and then a very quick, it's a shortcut to the computation of the wind force. But what I think is interesting here is to memorize in a way, to have a picture of the order of magnitude. Okay, I would say that we can make our break. And do you have any questions so far? Okay, as last Wednesday, I will now stop the camera and the micro, and I will leave the video running because it makes it simpler than to upload the video. So let's meet again in 15 minutes. Grazie, thank you very much. Okay, here we are. So, now, so orders of magnitude. The reference that you see here points out that a modern cargo ship with a tonnage of 30,000 tons, fully loaded, has a wind area of about 15 square meters per meter in the longitudinal direction, while the same ship in a ballast condition may have an area of about 20 square meter per meter. And this gives you an idea also of the difference between ballast conditions and loaded conditions, which is significant because we pass from 15 to 20. And large passenger ships have wind areas of about 35 square meters per meter or more. So this is, if you connect this information with the information given here on about wind pressure, you understand what is the order of magnitude of the force that you may expect, which is something that is to be compared with the tonnage that we mentioned for the bollards has an order of magnitude when we started the lecture. These are significant forces, and therefore you understand that on the one hand, we have to design carefully the bollards and also the structure of the berth. On the other hand, also the spring lines are exposed to forcing that is very significant. In fact, we will also discuss about spring lines, how to compute the mooring forces, which means the strength, the effort that has to be sustained by each spring line. Okay, so if the wind blows at an angle to the ship, which is the usual condition, by the way, because usually, as I said, we displace also the harbor in a way that we make sure that it is infrequent the situation when we experience the most challenging condition. In general, there is an angle between the wind direction and the longitudinal axis of the ship, which means that we have a longitudinal component and we have a transversal component. So, of course, if we want to compute the distributed load caused by the wind along one direction, we need to divide the overall forcing by the length of the berth in the length of the berth L2. And this is the distributed load. This is mentioned because, as you know, when designing structures, when we are allowed to, we distribute the loads because in general, the forcing given by a distributed load is less concerning with respect to concentrated loads. And indeed, when we talk about mooring forces, we are allowed by many regulations to distribute the load because we have several mooring points, we have several springs, and therefore we can simply divide the overall effort by the length of the berth. Now let's talk about each single mooring. The load that is caused by wind on each single mooring point, of course, depends on the wind forcing, the number of loads, and their position. And their position relative to the position of the ship, because the spring lines are usually inclined also along the vertical direction. They are not horizontal. And therefore, the displacement, the direction of the spring lines is highly influential. Indeed, in the harbors and also in nautics in general, we have rules for which give limits, which give an address, which tell us how we should displace the spring lines, how many of them and in which direction. And the purpose is to make sure that the load is distributed along several mooring points. But indeed, we are not discussing this in detail, but there are also some strategies, some design regulations that have to be adopted for giving the position for the placement of the single mooring point and the design of the close neighbor in the berth structure of the mooring points. In general, as you see here, proper reinforcing have to be designed to make sure that the load is effectively distributed along the berth length. We assume that the load is distributed, but we have to also displace proper reinforcing around the mooring points. And for piers where ships can berth on both sides, this of course implies that also the wind force may act on both sides. So the total wind load acting on the pier should be approximately the wind load on the largest ship plus 50% of the wind load on the ship on the other side. So we don't just sum the two wind loads. We are allowed by many regulations to decrease 50% the load on the other side. So we take the largest ship and we assume that the wind load is full on the largest ship, and on the other side we are allowed to reduce 50%. Now let's talk, as I said, about the mooring scheme. So this is a typical mooring scheme which tries to make sure that the ship is fully berthed, meaning that any movement is limited. First of all, here they are not shown, but there are fenders, which are kind of pillows made by rubber or wood that are placed between the ship and the berth. You see on the berth side the bollards, which are one extreme of the spring lines, and on the other side you have on the boat side you have also a fixed point at the other extreme of the spring line. Usually in the correspondence of the side of the ship, the spring line has an angle, and this point of contact between the side of the ship and the spring line is called chock. Let me just, in the nautical terms, let me be clearer, because C is here. Okay. Okay, let me see also. I don't see a picture, but okay, let me just do this. Chock ship. Okay, here we are. You see a chock here. The spring line going through the side of the ship through the chock. Okay, and this is another one. And here, in correspondence of the chock, you see that the spring has an angle, And when we compute the mooring forces, we have to take into account how the spring runs between the two extremes on the both side and on the ship side and the berth side. Okay, let's also look at this terminologies. Headline is spring line number 1, to keep forward part of the ship against the dock, and the counterpart is number 6, the stern line, which prevents forward movement. So these are the two extremal lines, and then we have these lines that are perpendicular to the berth. They are called forward breast line and aft breast line. They serve to keep the ship very close to the pier. And then there are the two forward spring and aft spring, which further contribute to prevent the movement of the ship in a parallel direction with respect to the piers. Usually, these spring lines are in a varying number. Of course, when you have small ships, you have less than that, but for big ships, you may have also more than that. Okay, and then in general, the action of wind generates. What I am discussing now, I am slowly moving forward to the computation of the mooring forces. So we understood how to compute the wind force. We saw that it has a longitudinal component and a transversal component. Now, given these components of the wind force, we have to move forward the computation of the mooring forces, which means now passing on the ship side, taking into account the position of the spring lines, and this is why we discussed the spring lines, taking into account their slope, their inclination in the vertical direction and in the horizontal direction, taking into account the position of the chocks, taking into account elasticity of the spring lines, and then computing the mooring forces. The mooring forces are needed for designing, first of all, the cross-section and the features of the spring lines in general, and designing the reinforcing around the bollards, around the mooring points on the berth. So now we have to understand what is the dynamics, the dynamic reaction of the ship to the wind force. Of course, the ship is hit by wind. The ship is a rigid body, and the wind generates a drift and a rotational moment. The drift is a push along the direction of the wind, which may have two components, one that is parallel to the berth and one that is perpendicular to the berth, and then there is rotation. Rotation, even in absence of the drift, rotation means that the boat, if it is supposed to be unmoored, completely free, doesn't move back and forth, but rotates. And this generates, of course, if the ship is moored, generates mooring forces by itself. So we have to understand what is the feature, the dynamical feature of the drift, and what is the dynamical feature of the rotational moment. So what is basically driving this possible two movement of the ship? Of course, the wind force, but what is really important to understand also, in particular, the rotation, is the action of the wind force, the point of application of the wind force, which is in the center of gravity of the exposed area, and the position of the pivot point. So what is the pivot point? It is the point around which the ship appears to be turning for an observer standing on board of the ship. So this means that if you stay on board of the ship and the ship rotates, there is a position where you feel that you are just rotating and not moving. This means that we are above the pivot point. So the pivot point is a geometrical feature of the ship. So let's try to better understand. For a resting vessel, the pivot point, how can we locate it? It is located in the center of gravity of the underwater body of the ship. And you may understand this because basically what hosts the ship is water, of course, and water is acting on the ship with a pressure. And this pressure, of course, is given in the underwater body. And this pressure is basically distributed with similar features on the underwater body, which means that is dictated essentially by the depth of water that is acting over any point of the underwater body. And therefore, this pressure of water over the ship is applied to the center of gravity of the underwater body. Which means that, in a way, this is the reaction that water basically act against a movement of the ship, which is applied in the center of gravity of the underwater body. When the ship is resting, because when the vessel moves forward, the position of the pivot point shifts forward when it's moving forward. And so for typical velocity of vessels, here you can read, the pivot point will move to about 1/4 of the length of the vessel from the forward. And when it's moving backward, it's the same, but in the opposite direction, basically. So we are interested in the position of the pivot point when the vessel is resting. So rotation is originated when the center of gravity of the windage area, which is the windage area is the part of the ship that is above water, it's not located in the same horizontal position with respect with the pivot point. So of course they are located in a different vertical position, but if they are on the same vertical, there is no rotation. Instead, if the pressure of wind is eccentric with respect to the pressure of water, you get rotation. Okay. I think there is a figure, but let's see later on the figure after this slide. So let me just, no, because let me move forward and see the figure. Okay, let's wait for it. Okay, so at this point, I think we can, for now, pause the discussion of the wind-induced movement and wind-induced forcing, and we can pause the discussion of the computation of the mooring forces due to wind. Why? Because I plan to make an exercise of computation later on. I think that the best way to understand how to compute the mooring forces, how to compute the rotational moment, which will depend on the eccentricity that we just introduced, how to compute the longitudinal and transversal component, I think the best thing is that we refer to an exercise. I have an exercise that you can already see on the web pages. There is a link, and my plan is next Wednesday to start making this exercise, maybe in the second 2 hours, so that we can understand in practice how we can move forward from here. And so for wind forces, I think that for now we can pause the discussion, and then we can pass to wave forcing, which is treated in a similar way, and it will be treated with a shorter discussion. Any question related to wind-induced movement, wind forces? Okay. So, wave forcing. Waves they tend to move the ship, and therefore they give a forcing on the mooring points. So waves in the proximity of ports, of course, waves into the harbor, which are very different from the open ocean waves. These waves into the harbor usually bring less energy with respect to the open ocean waves for obvious reasons, because the harbor is a sheltered area, because we try to protect the entrance of the harbor in order to minimize the action of waves, because in general, what you expect in an harbor is to find calm conditions, because for obvious reasons. However, it may happen that we may experience waves also in the harbors, also important waves, especially if the harbor is important in itself. If the harbor area is extended with a large entrance, it may happen that waves from the ocean get into the harbor. There are also waves originated by the movement of ships. We will also dedicate a separate lecture to the analysis of a phenomenon which is particularly important, which is wave resonance inside an harbor. I think you can already understand what I'm talking about, meaning that when waves get inside an harbor, they travel towards the berth and are reflected by the berth. And the time they take to travel back and forth depends on the geometry of the harbor, depends on the wave celerity and the length that they have to cover, essentially. The reflective wave basically keeps its energy. It's okay, there is some energy loss during the reflection, but it's very limited. It's limited because usually in the harbor we have huge depth of water, which doesn't help to dissipate energy. And therefore the reflective wave have a similar feature like the incoming wave. You understand that when the reflective wave sums over the incoming wave, it may happen that the two amplitudes sum up. And therefore, the wave gets transformed and possibly amplified. It depends on the geometry of the harbor. And then what happens when the wave back travels back to the ocean? It can be, depending on the time, on the travel time, it can be reinforced by the waves coming from the ocean. So basically, if the two waves, the reflected one, which is already amplified, and the incoming wave have the crest in the same position, the through in the same position, then it may be that they reinforce each other. So it has been observed that in particular conditions, these waves, this superimposition of waves may generate resonance, which means that the wave amplitude keeps increasing. We will dedicate a lecture on this problem because it's interesting, and I would say that it's also fascinating. It is something that in particular conditions, it's a matter of concern. Anyway, let's try now to see what happens when we get the waves into the harbor. The waves are forcing the moored ships, and let's see how we can compute the forcing originated by waves. First of all, we have to monitor the waves and get information, inductive information on their behavior. And if we don't have information and we have to be involved in a project like restoring an harbor or designing an harbor, it's a very good idea to start monitoring waves as soon as possible, because at least, I mean, you know that when we talk about wave monitoring, to get a meaningful definition of the wave characteristics, we need at least 1 year of observations. 1 year, it's a long time, but at the same time, if we think the time taken by a project and the time taken by building an harbor, realizing an harbor, it's not really a long time. And if we start as soon as possible to get information, by the time that we start building the harbor in practice, we may have additional information to assimilate. And this is extremely important in order to minimize uncertainty. Let's say that how long is a satisfactory observation period? For the purpose of defining events with the typical frequency that is used, the typical return period that is used to design berths, 5 years is already a good timing. Keep in mind that fenders are designed with a return period of 10, 20 years, and berths may be designed for a return period of 30 years. If it depends, of course, on the impact that a collapse may have. But if for structures that are not involving a real danger for the human life in case of flooding, usually the return period that is used is about 30 years, with some exceptions for critical situation. So when you have 5 years of data, it's already a good piece of information. Now, first, when we talk about wave forcing, we should avoid wave breaking into the harbor. You know what is wave breaking? Wave breaking means that the transfer of energy, the wave is usually a transfer of energy. When the wave breaks, the transfer of energy becomes a transfer of mass, involves also transfer of mass. So we have to avoid wave breaking into the harbor. So the first thing that we have to study is, basing on the behavior of the wave, to study, to design the depth of the harbor, not only basing on the route of the ships, and therefore not only basing on the type of ships that we expect for the harbor, but we have also to take into account that we need to avoid the breaking. And as an empirical rule, you can use the simple expression that you can see here. And dB is the sea depth at the breaking, and HB is the individual wave height at breaking. Height is twice the amplitude. So this means that once that you have a difference, you have estimated the difference between the wave crest and through, so the height, the depth, and this is to be estimated for a return period that is adequate to the design of the harbor. Then you have to take a depth of the ocean that is at least 1.3, the max height that you are expecting, in order to avoid the breaking, because the breaking, it is indeed multiplying the action that the wave may provoke over the ship. Usually, anyway, when we take into account the wave forcing, the wave height that we adopt is usually reduced with respect to the design wave for a given return period. In fact, I told you that the return period that we may take is about 30 years. And it is reduced because it is true that wind forcing may superimpose, may occur at the same time as wave forcing. But There is to say that the wind loads are usually much higher than the wave loads. And therefore, once that the structure is designed, I mean, the wave forcing is not very significant when it is summed to the wave forcing, to the wind forcing. And usually when we design for the wind forcing, we adopt a coefficient CW, which, by the way, now I realize I didn't mention because I followed the slides. I have to go back a little bit once I finish this reasoning. So there is the coefficient CW that is already a safety coefficient, which is significant. And therefore, there is no need really to sum the full wave forcing. It doesn't make a big difference, even if we sum the full of it. But on the other hand, usually guidelines say that there is no reason to assume that they are fully concurrent. There is to say that if we adopt a reduced wave height, we expose the berth to the risk of flooding. So maybe that the mooring point, they are fine, but the berth is flooded. So it is not a problem in principle, unless it implies a risk for the humans. So we can also take the risk of the berth being flooded, and we have to take into account that if the berth is flooded, of course, the loading, the mooring operations may be interrupted, but it is not really a big problem. So, I mean, the moral of the story is that when you already designed for wind forcing, for wave forcing, you may, in a way, decrease your safety factor, always by looking at the local rules. You know what is inducing, what is determining the characteristic of waves. And let's forget about this for now, because I'm sure that you already know all of these features of wave dynamics. And also we will discuss resonance in a separate lecture, as I said. So let's just forget about it. And then let's talk about the return period for the design wave. I could have talked of the return period also for design wind. So it is the same. It is the same discussion. It is the same concept. So what is the return period? First, make sure that you know the definition, because this is very important. This may come out at the exam, and it is a definition that usually students report in an imprecise way. So it is the average time lapse between two consecutive events with an intensity reaching or exceeding a given threshold. With intensity, I mean wave height, for instance, but it could be wind velocity. So, what is important in this definition is not to forget the term average. The return period is not the time lapse between two events, equaling or exceeding a given threshold. It's the average time lapse. This seems to be a nuisance, but actually it is extremely important, especially in communication with the stakeholders, because when we report to stakeholders that an event occurred with a return period of 50 years, they tend to assume that for 50 years they are safe. This is not true. I mean, average is 50 years, which means that two events exceeding or equaling that event may occur after 1 day. It's, I mean, it's the average that is 50 years. So just remember this definition, don't forget the word average. The return period is a concept that in engineering is widely used. The return period is equivalent to probability because it's equivalent to frequency, and therefore you understand it's equivalent to probability. So when you talk with the statisticians, they don't know the term return period. They just talk about probability. A return period implies that your data are collected as a function of time, which is perfect in our case because we are talking of waves, wind, observations, so they are recorded at a certain time. Statisticians talk about probability or frequency because their observation may be something like tossing a coin, which is a function of an index, I, toss number 1, toss number 2, but not of time. So just keep in mind that it is a very technical term, it is a very technical concept that we use widely in engineering, also for earthquakes, for many natural hazards. We talk about return period, because indeed we are interested in the time that may pass before we get a similar damage, because of course it is very relevant for computing the average damage. It is very relevant for computing our expectation. So the return period, it is often a parameter for the project, for the design, which is often given by the law in force. So there are several regulations determining the return period for structures, infrastructures, several engineering applications. The return period is a measure of the risk. Let's say that it contributes to determining the risk. It's not the only driving force of risk. What is risk? Risk is an expected damage, which depends on the frequency with which you expect an event, the return period, and the risk also depends on the value of the goods that are exposed. So if there is no damage at all, if an event occurs, there is no risk. If the event is impossible, there is no risk. Risk comes from the combination of likelihood of an event, so hazard, it is called hazard, and the value of the exposed goods. So the return period, as I said, is directly related to risk. And this brings us to easily understand that when the human life is threatened, then the return period must increase. If we are talking only of an economic damage, then we can accept more flexibility in the definition of the return period. Because of course, when you design something, if you want to oversize it, which means that our infrastructure can resist against an event with an higher return period, but if you oversize it, you need money. Accepting that an infrastructure is not working during an extreme event, which may be frequent, implies a damage, an economic damage. And therefore, people, if there is no human life at risk, may evaluate the cost and benefit, you know. And so it's a different reasoning. So when human life is at risk. So let's keep this difference very clear. I mean, also in terms of return period selection, but also in terms of our conceptual approach to design. It's a different story. And in fact, this may seem like something trivial, but it's not, because if you think of insurance companies, they monetize everything because they basically need to monetize also the value of the human life because they insure also human life. And therefore they need to monetize it. So they are very used to monetize everything, but in other fields, and also I would say in engineering, it may be close to unethical if we treat the human life by giving a value to it. It's a different thing because we are asked to design an infrastructure, design something for a certain purpose, which is not the economic budget. The economic budget is something that is part of it for us. Of course, we have to look at resources needed, we have to look at the costs, but it's not only that. For an insurance company, the insurance company is not designing. They are asked to give money back if somebody dies. So, of course, they have to monetize it. For an engineer, you have to be careful because monetizing the value also of natural resources may be close to unethical. For instance, if you monetize the environmental impact, you have to be careful. And because they are natural resources, you give a value to them, but the value may be intangible for some reason. Of course, we can give a value to the human life, but you understand that from another perspective, which is not the perspective of the insurance company, the human life may be something intangible, which means that you cannot really give a value to it. So you have to just be careful. But in general, you have to look at regulations. Regulations give you indications or restrictions or formal constraints. You can increase the retro period if you see that this is not really a problem to oversize a structure. You cannot decrease it. Okay, and so determination of the retro period. We need to understand some more because in some cases we may ask to give our contribution to that. And the retro period, some people basically think that should be the same as the expected lifetime of the structure. This is not really true, and it's not necessarily the same. It is comparable in general, but not necessarily the same. I give you an example. For dams, the expected lifetime of a dam is no more than 100 years. There are some dams that we may expect that they work for hundreds of years, but actually, if you think of the duration of the concrete, if you think of the siltation of the reservoir, there are dams that after 50 years cannot be used anymore. So it's about okay, let's say 200 years, the expected lifetime. The return period is imposed by our national regulations to be at least 500 years. Why? Because there is a high risk for humans. And so we fall back in the reasoning that I just made. And also, there is a mathematical reasoning that we can make, which help us to understand the relationship between the expected lifetime and the return period. So, are we willing to accept that during the expected lifetime, one given event occurs with high probability, or we want to reduce the probability? Because if we want to reduce the probability, we have to increase the return period with respect to the lifetime. And so let me just explore and let me compute. Let us compute now, because it's an interesting experiment. What is the probability that the wave height, here there is a spelling error, with probability P is exceeded during a period of n years? So let's try to understand what is the relationship between the probability of an event, which means the return period. Like, let's see what is the probability that an event with a return period of 100 years occurs in 100 years. The probability is not 1, because we are talking about an average, and also you cannot say that you are sure, you are certain that in 100 years an event with a return period of 100 years occurs. So what is the probability? Okay, so first of all, let us recall the relationship between probability of not exceedance and return period. So this is cumulative probability, probability of not exceedance. So let's refer to wave height. I'm sorry, here there is no highlight that the probability is function of something like wave height. I should have written Px, where x is wave height. This is equivalent to t minus 1 divided by t. For instance, if you have a return period of 100 years, the probability of not exceedance is 99%. Good. Then the joint probability that the given wave height is not exceeded in n years is computed by elevating the probability to the power of n. So P is equal, the probability of which refers to 1 year to the power of n, okay? From which it's possible to get an explicit expression for t, which is what you can read there. It is a simple development. And if we put into a graph here, the lifetime of the structure and the return period of a given wave height, we see that for instance, if we look at the lifetime of the structure 200 years, return period 200 years, we get a probability of 63%, which means the same if we look at 100 years. So it means that there is a 63% probability that the event corresponding to a return period of 100 years occurs in 100-year lifetime. This is an interesting consideration. And of course, if you change the probability, if you want a lower probability, it means that if you want a lower probability, like say 50%, that in a return period, in a lifetime of 100 years, the given event occurs, you have to adopt a return period of 150 years. And if you go to 1%, which means I want to be reasonably sure, 99% sure, that during the lifetime that event doesn't occur, I take a lifetime of 20 years, I have to go to a return period of 2000 years. This is quite, I mean, interesting, and it is something that is often overlooked. Okay, let's give some numbers, and keep in mind that in the previous lectures, I already gave some numbers for the design of births, numbers in terms of return period for the design of births. So when designing birth structures, it is usual practice to adopt a return period for the design wave of at least 100 years for birth structures. But for some components of it, and in some particular situation, as I said, we can reduce it. And in any case, the return period should be not less than the design life of the structure. The design life of a birth is around 30, 50 years. It depends, of course, on the birth, but the reason why the design life is kept so short is that these structures are frequently exposed to corrosion, to deterioration. So it is unlikely that a birth lasts for more than 50 years unless it is really built. It may happen for important harbors with very costly protection and with careful evaluation of the durability of the structure. Okay, and but of course, as you can see here, if the impact from a failure of the structure is unacceptable, then of course the return period may be increased and reach the return period that is used for dams, for instance. So basically, you can refer for the structure to 100 years as an indication, which can be decreased to 50 or even 40 years for structures where you don't see a long durability and you don't see a huge risk if they are flooded or if the mooring points may fail. Because, for instance, you may predict the possibility, the plan B and plan C, which I mentioned before, to unload the ship, to load ballast or to unmoor the ships in particular conditions. Okay. Wave direction. Keep in mind that when you compute the wave height, you refer, like for wind, you refer to a wave direction. So we have to consider any wave direction, and in particular, the wave directions that could be more impacting. For instance, the waves that are perpendicular, the wave direction that is perpendicular to the berth. We will try to displace the berth parallel to the dominant wave direction. But in any case, what is reported here is that you have to carefully consider for both winds and waves, and we will see also for currents, we have to carefully consider also the issue of direction. I think there is not much to say here. And so what is the rule of thumb for waves into an harbor? It depends on the ships, of course. And again, the Spanish standard suggests that if the ship has up to 3,000 tons of tonnage, these are the rules of thumb. So for small ships, we can take a wave height of 0.4 meters. You see that these are very reduced because I already mentioned that within an harbor, we expect a reduced wave height. For fishing vessels, 0.6, and for fishing vessels that are particularly long, longer than 30 meters, we get to 1 meter. And overall, with ships with higher displacement, we can go to a couple of meters, but this is to be considered like an extreme, really extreme value. And it is when there is the feeling that a similar situation may happen with waves that may reach 2 meters of wave height, it would be better to consider how and where to displace some protections in order to mitigate wave propagation. Now, here it's time to talk about the movement, the possible movement. Talk once again about the possible movement of the ship. The ship is a rigid body with 6 degrees of freedom, which are represented here. And they correspond to translation along the 3 directions and rotation around the 3 directions. Of course, depending on how the ships move, we compute the mooring forces. Let's focus on some terms. And so, rotational and translational motion, 3 axes around which the ship can rotate and along which the ship can move. So the longitudinal axis, the transverse axis, and the vertical axis. So the rotational movement around them are, respectively, roll, pitch, and the yaw. So basically, you see the yaw is a rotation around the vertical axis. The pitch is a rotation along the transversal axis. The roll is a rotation around the longitudinal axis. And the 3 movements along the axis are sway along the transversal axis. So it's translation in the direction of the transverse axis. Surge is movement along the longitudinal axis, and heave, movement along the vertical axis. Just remember, please, these terms, because they are frequently used also in the guidelines, standards, regulation, etc. So, some additional orders of magnitude. Mooring line forces are induced almost entirely by waves of period longer than 20 seconds. Because if 20 seconds is the order of magnitude of the forcing to develop along the mooring lines to get fully stretched. So if the period is lower than that, the elasticity of the mooring line mitigates the forcing, with major contribution occurring in the period range 40 seconds, 3 minutes. more or less. You may think that waves with a period of 3 minutes are not very dangerous because it means that the amplitude is not really much extended, much large. On the other hand, keep in mind that the waves that can cause resonance are precisely those with the longer period. It's the long wave that can undergo resonance. So this is why major contribution occurring in the period 40 seconds, 3 minutes, the waves with period of 3 minutes can indeed resonate, and therefore their amplitude may increase. Rolling is triggered primarily by swells with a period in a shorter range. Pitching is small and insensitive to the wait period, whereas heave motions tend to equal the wave height at long periods and are smaller with short period waves. I'm not asking these notions, this indication at the exam, but my suggestion for you, try to get this concept, try to elaborate in your mind these indications, because these give to you an idea of how the process develops, how the process features, and it gives to you an idea on how it works. Okay, and the best thing would be that you go into an harbor, maybe in conditions that are not very calm, and see how ships move. I found this very interesting. After you, in a way, you gained these indications and made this concept well established in your mind, I think I found it very interesting when you see that there is some nervous sea, to look at an harbor, at moored ships, and see what happens, depending on the size of the ship. Keep in mind also that the ships have their own frequency of oscillation. And therefore, of course, large ship has moves, oscillates with a longer period, with a lower frequency. And therefore, it's more sensitive to waves with longer period. And it is interesting to see how they compare the ships depending on the size. And once that you got it, your design work becomes easier, because it gives to you the intuition, and then you have the capability to check the results to understand if you did a good job. Now, let's look at the formula, and I think we are moving towards the conclusions for today. Here, again, we have lateral on transverse wave force in kilonewton and longitudinal wave force in kilonewton. And what you see here, it's a very similar structure with respect to the empirical relationship that we used for wind forcing. One thing, while for wind forcing, I asked you to make an effort to learn it. For this one, I'm not making the same request, because I think it's better to concentrate on just one. And here, what you can notice is that while when we analyze the formula, when we discuss the formula for wind forcing, the forcing that was dependent on the square of the velocity, because the square of the velocity for the wind is representative of the energy of the wind. Here we need a similar term, and because the forcing must be proportional to the energy of the wave. And in fact, we have here wave height squared, which, as you may remember, is proportional to wave energy. So basically, this is the energy component that we find here. The square of the wave height. And then we have gamma W, which is the specific weight of water, which is the analog of the gravity of air that we considered for the wind forcing. And then we have the sin square and cosine square of the angle phi. The angle phi is the angle of the wave direction this time to the ship center line. And then we have D prime, capital D prime, which is the projection of the ship length in the direction of the incident wave, which is given by the length between perpendicular. You see that it comes again and again, this nautic term, multiplied by, you have to look at the last but two lines, length between perpendicular times the sin phi plus b, which is the beam of the ship, cos phi. So this is the projection of the ship length. And then we have two coefficients, which are the water plane coefficient, which depends on the wavelength, and the ship's draught. I don't know, the pronunciation I think is draught. And then we go to my web pages to see how to determine this water plane coefficient. And then we have a depth coefficient depending on wavelength and the water depth. Now, in our discussion today for wind forcing, we called into play CW. Here we are calling into play two coefficients, CFW and CDW. Let's discuss how to estimate them, because I forgot to do that when I discussed the wind forcing. So let's move to the web page, because we have here a couple of graphs which we can refer to. Just 1 second. Okay, here it is. So now let's go at the graph for CW. Okay, no, there is no graph here. Just let me increase the font. The magnitude of CW depends on the shape of the ship. We are talking about the wind coefficient here above water, and the orientation of the ship has average value for isolated ships. The following values are recommended. For wind crosswise to the ship, CW is 1.3. Crosswise means the wind hitting the longitudinal axis perpendicularly, so the worst condition. CW 1.3. For wind against the bow, it's 0.9. And for wind against the stern, which is the forward part of the ship, 0.8. Okay, so you see that in the worst condition, we have a safety factor of 30%. When the wind blows in the longitudinal direction, we can decrease it. The reason is that, remember, when we computed the wind force, in the longitudinal direction, we took the transverse area projected in the transverse, across the longitudinal direction, so projected over a plane, which is perpendicular to the longitudinal direction. But actually, the boat, the ship, is shaped in a way to minimize resistance to wind. It's not the wind when it blows in the longitudinal direction, it's not hitting perpendicularly to the surface of the boat. So this is why we have a coefficient of reduction, which is lowering the wind force, because it takes into account the fact that the ship is shaped in a way to get into water, into a fluid, by opposing the minimum resistance. The ship is conceived to move in the longitudinal direction, and therefore there is less resistance to the fluid in the longitudinal direction. In the transversal direction, there is instead more resistance, and this is why in one case you have to increase the forcing to introduce a safety factor, 1.3, and then when you are in the longitudinal direction, you don't have this need. And you understand why against the bow you have a higher CW coefficient with respect to against the stern, because the stern is the part of the ship that goes forward into the ocean. There is the minimum resistance there. Okay, this is for wind forces. Now, wave forces, these two coefficients, CWD and just 1 second, here we are. CWD, CDW and CFU. We have here two graphs, let's say, abacuses. I think in plural we say abacuses, but okay, there is an abacus for CFW and an abacus for CDW. And you see the values. CFW actually is very low, and CDW, it's in general, it's higher than 1. And the independent variable is a combination between pi, D, which is drought, H, let me just see because I don't remember, D is drought of the ship, H is water depth at the location, and LW is wavelength at the location. Of course, I mean, as I said, you don't have to learn by memory. If you just try to make an effort to remember the structure, how it is structured, this formula, what is it? It's here. And the longitudinal wave force, it's similar. It's the same formula with the sin exchanged with the cosine. So it's more or less similar. I go back here. And that's it for wave forces. The two abacus are here. Good. I didn't remember that I put them here. Okay. Now, currents, very quickly. This is just, we don't discuss it. This is for you to have a look. And I just want to say a few things about currents. First, they are not a big problem. I mean, with the exception of particular situations, which are the situations where along the coast you may experience significant concerning currents, typically in the ocean front, or in a situation where the harbor cannot be sheltered, in situation where you have a high tidal excursion, then you may have currents. So with the exception of very specific situations, usually currents are not a big issue. And as I said, wave forcing is normally not a big issue as compared to wind forcing. And the same can be said for currents, even less than wave forcing. So, as I said, unless there is a particular situation which requires particular care, and usually you know when it's the case, this doesn't really implies a significant additional forcing. There is a reasoning that is more or less the same from a physical point of view of what we did with wind forcing and wave forcing. Keep in mind that current is a movement of mass. Current is not like the waves. The waves, it's a movement of energy. Current is a movement of mass. And therefore here, the forcing must be proportional to the velocity of the mass. And in fact, you see the velocity square here, Vc is the current velocity. The current velocity changes with the depth of the sea. So here there is also the indication of where you have to compute the velocity. And then there is the density of water. It's a similar approach with some coefficients and with the area, the submerged area of the ship that matters here, and also the angle. So it's just enough if you remember that the principle is the same. The main difference with respect to waves is that the energy is represented by a velocity squared and not an height squared. But I don't think that we have to discuss much. I just wanted to give you an order of magnitude, what could be the velocity of a current. It's not a huge velocity. It's about, it can range between 1 and 2 meters per second, which is not, I mean, it is significant, but take these values as already very significant values. And these are the values where, when you can find a significant additional forcing. But if you make a simple comparison between the energy that is conveyed by a wind forcing, and you have estimates because you have an estimate of the pressure, and you estimate the pressure here with a velocity of the current of 1.5 meters per second, you understand that the comparison is unfair. Okay, it turns out to be not very significant. Okay, and good. This presentation is finished. Just let me go back to the web page. Yeah, there is something. I remember that there was something that I wanted to discuss, which is the impact of ships. So my premise was we are not considering it. So there are only a few lines dedicated to it. And it is an accidental load. It's not negligible. I mean, if you consider the frequency of this kind of accident, they are not so rare, and they are an important cause of damage for the berths, for the piers, and this is why there is a lot of attention on ship maneuvering. This is why the traffic is controlled, and this is why there are limitations, etc. Basically, I mean, this is something that has to be considered. We are not discussing it, but not because it's not important. Indeed, it can turn out into a significant forcing. Just take into account that the energy that it's transferred from the ship to the berth depends again on the square velocity of the ship. So it is extremely relevant to respect the speed limits in the maneuvering. On the other hand, there is to say that, you know, sometimes in windy conditions, it may also be difficult to maneuver. Recently in Venice, an accident occurred with a ship, a big ship, sorry, which experienced a big ship, which was the collision with the berth. You may remember, I think it was a couple of years ago or last year, and there was a significant damage. And a rule of thumb suggests that you have to consider in normal condition, there is an energy that is given by the ship against the berth. And this energy that is used, this impact force is used to size the fenders and to determine the material of the fenders. So you have to consider that at least the energy transferred by an accident is at least twice the energy that is transferred in normal condition, at least twice. And you should consider for determining the forcing what are the limitations due to speed limits And also, in some cases, you have to also consider the wind speed, because in the presence of likelihood high wind speed, you have to be careful about the influence and the impact of this kind of accident. I just wanted to spend a few words because if you look on the references that I made available to the impact of ships, I dedicated a long chapter. It's empirical formulation, so really I was not motivated to include a long discussion here. I think that this is fine. Okay, any question? Everything is fine. Okay. So I want to thank you very much. Let me thanks Shada if you're still connected. And thanks Giorgio. I close the registration. Okay, perfect.